Welcome back, everybody, to episode 38 of the Quantum Science Seminar, which will be about continuous Bose-Einstein condensates and superradiant lasers today. As usual, we'd like to have your questions. Please send us your questions to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of the screen. I should also note, as usual, there's a 30-second time delay between what you see on YouTube and between what we do. And with this, I'd like to hand over to Christian, who will introduce our speaker today.
Yeah, welcome everyone, also from my side. We are very happy to have Florian Schreck speaking today at the Quantum Science Seminar. Florian is a full professor at the University of Amsterdam with world-renowned expertise in the field of ultracold quantum gases. He's currently working on 4 projects, just to give you an idea what is hot in his lab right now. That's one aiming at the realization of the world's first continuous atom laser, and we will hear today about that. One on creating rubidium-strontium ground state molecules, one on quantum simulation based on strontium atoms in optical tweezers, and one on a superradiant strontium clock. The latter is actually part of the iqClock project, which is in fact coordinated by Florian. It is one of the few quantum flagship projects of the European Union. Florian received his PhD from ENS Paris, where he pioneered lithium quantum gas mixtures in the group of Christophe Salomon. Afterwards, he moved for a postdoc to Mark Raisin's group in Austin, Texas. And then from 2004 to 2013, he worked as a senior scientist in Rudi Grimm's group in Innsbruck. In Innsbruck, he actually pioneered ultracold quantum gases of strontium. And that was the element you basically heard 4 times when I read his projects, I think. That element is actually seeing ever-growing popularity among us AMO researchers since Florian basically brought it to the family of degenerate gases in Innsbruck. And then since 2013, he is full professor in Amsterdam and continuing his research with strontium. And with that, I'm happy to hand over to Florian and very curious about news from his group.
Thank you, Christian, very much for this nice introduction. And it's a great honor for me to speak in this famous seminar series about continuous wave BECs and superradiant clocks. And these 2 projects are in the field of quantum sensing. So let's start with discussing the difference between classical sensors and quantum sensors. Imagine you live 200 years ago and the king orders you to build him the best clock in the world. Then you would most likely use a pendulum as your frequency reference. And these pendula are man-made macroscopic objects. You will never be able to build 2 that tick at exactly the same frequency. And then one day the king will be late to his appointment with the queen, and then you have a problem. Luckily, we live in a quantum world, and the quantized energy levels of atoms provide us with ideal frequency references, namely the frequency of the electromagnetic radiation that's needed to drive transitions between these levels. And if you want to build a very good clock, you should choose an atomic transition with a high frequency and narrow line widths. Optical transitions with millihertz line widths would be nice. You want to have a large signal from your atoms, so you should use many atoms, but don't put them too close to each other. That will shift the line around, so you use a guess of atoms. And now you have to take care of the Doppler effect, which also would shift the frequency around. So you need to cool these atoms to essentially stand still. And you do this inside such vacuum chambers as this one. We have here an oven where strontium is heated up such that an atomic beam effuses from the oven and travels with a few hundred meters per second velocity through the chamber. It's slowed down by absorbing photons from this counter-propagating laser beam, and then we use more laser beams to push the atoms into the center of the vacuum chamber and cool them more inside this Magneto-optical trap. And then the atoms are cold enough that you can trap them in a so-called magic wavelengths optical lattice like eggs in an a carton, and it's called magic wavelengths because it doesn't shift the clock transition frequency around. And you can spectroscopically interrogate the atomic transition and block your laser onto the atomic transition. And that's your optical clock. Some people don't like clocks that tick at 400 terahertz, such as this one. Those people then can just buy an optical frequency comp to translate this frequency to whatever frequency they desire. Ultracold atoms are also good for atom interferometry, which work similarly to laser interferometers. You take your atoms and split the path of each atoms onto two paths and make the atoms interfere with each again after a while. And unlike photons, atoms have mass. That means these atom interferometers are exquisitely suited to detect acceleration or rotation. And also here you profit from ultracold atoms because during the interrogation phase, the atoms must be in free flight. And if you have a hot cloud of atoms, they would fly away sideways and you couldn't interrogate them for very long. The colder the atoms are, the longer you can interrogate them. These ultracold atom quantum sensors have many applications. In fundamental science, you can explore physics beyond, or look if there is physics beyond the standard model, test relativity, ask yourself if the fundamental constants of nature change, and so forth. Inside these devices, there's also interesting and subtle many-body physics going on that you are sensitive to because these quantum sensors are so precise. In the future, we might be able to build infrasound gravitational wave detectors or enable even longer baseline interferometry. And for society, we can use these devices for network synchronization, navigation, underground exploration. We want to contribute to this field, and we do this with two projects. In one, we try to build a continuous wave atom laser, and in another, a continuously operating superradiant clock. And here this diagram shows you how these projects are related. On our way to a continuous wave atom laser, we recently created a continuous wave BEC, a BEC that exists for as long as we want in steady state and flow equilibrium between loss going on in the BEC and new atoms put into it. For that, we created a microkelvin called strontium beam in the dark, and that's ideally suited to provide a gain medium for these continuously operating superradiant clocks. And now I will start in the first part of my talk with describing the continuous wave atom laser project. So what is a laser? A laser is a propagating wave that describes many particles, an electromagnetic wave that describes photons, or a quantum mechanical matter wave that describes atoms. And lasers are very good for atom interferometry, much better than thermal sources of photons or atoms because they have higher brightness, lower divergence, easily a better spatial mode structure, large coherent lengths, and potentially they're useful for squeezing. And that has been long exploited for optical interferometry, but not that much for atom interferometry. And one reason might be that there is no continuous wave atom laser yet. And we are trying to change this. So what do you need if you want to build a laser or extract a laser beam? The simplest model of a laser is you take in the optical domain is you take an optical cavity, you fill the ground mode of this cavity with lots of photons, and then you make one mirror a little bit transparent and let the photons leak out. And you can do the same thing with atoms. You cool a gas of atoms in a trap so much that most of them condense into the ground state mode and form a Bose-Einstein condensate. And then you punch a hole into your trap and let the atoms triple out, forming an atom laser beam. Now, of course, you will eventually run out of particles in your cavity in your trap, and the atom laser will extinguish. And for the BECs, you even have more trouble. Even if you don't outcouple atoms from the BEC, it will not live for all that long because there's a three-body recombination leading to molecule formation going on in your BEC, or trap shaking could heat it up and such nasty effects. So normally BECs don't live for much longer than a few 10 seconds at the best. And we want, of course, to have laser beams that last for very much longer. So in optics, you put an inverted gain medium into your lasing cavity, and then stimulated emission will amplify the electromagnetic field in the cavity. And the equivalent for an atom laser is to put a thermal gas of atoms into your trap that is at very high phase space density, so that elastic scattering, Bose-enhanced scattering, drives atoms into the BEC mode. Now, this will let your atom laser live for a little bit longer, but eventually, of course, also those atoms will be gone. And to go beyond that, you need to pump your laser optically, for example, keep up the inversion for an optical laser. And the equivalent for an atom laser is to put a continuous stream of ultracold atoms into your thermal gas. And it's important that this thermal gas in the trap is able to irreversibly accept these incoming atoms that replenish the thermal gas. And so you need some dissipative process, and we do this by a little bit of laser cooling in the thermal cloud surrounding the Bose-Einstein condensate. Now, this is the plan of our project, and so far what we achieved was to maintain a BEC around for as long as we want. We call it a continuous wave BEC, or BEC in steady state and flow equilibrium between loss and pumping. Good. Let's take a look at the history of atom lasers. There are atom lasers out there, pulsed atom lasers. They are made by first laser cooling, then evaporatively cooling a cloud of atoms till you form a pure BEC. Then you punch a hole into the trap and outcouple an atom laser beam, as I explained before. Eventually, you will run out of atoms. And yeah, that's a bit troublesome if you want to use it for precision measurement. You now need to create a new Bose-Einstein condensate, which takes a few seconds or tens of seconds to create the next atom laser pulse. And the pulse doesn't last very long at a decent flux, perhaps a few hundred milliseconds. And if you want to use this for precision measurement, that has disadvantages. Each time the pulse stops, you lose your phase coherence. The pulsed operation of a measurement device introduces noise through the Dicke effect. And by executing all these cooling stages one after the other in time, you of course obtain a lower average flux than what you would like to have. Now, an obvious solution to this is to execute all these cooling stages not at the same time distributed over space. And great strides have been done over the past 20 years or so to create a continuous wave atom laser. Wolfgang Ketterle's group created a Bose-Einstein condensate, transferred it to a second vacuum chamber part, and then while it was slowly decaying, created a new BEC, which they shuffled over, and then they merged these two independently created Bose-Einstein condensates. So they always had a Bose-Einstein condensate in their system. However, this merging was a little bit violent and created phase and atom number fluctuations, and that's possibly the reason why so far this didn't lead to a continuous wave atom laser. David Gary-Audelin's group and Georg Reichel's group pioneered continuous evaporation of a beam streaming down a guide. John Close and Nick Robbins' group proposed and demonstrated a new pumping mechanism to uphold PECs, and Tilman Faust and Griesmeyer's and Carsten Klem's group pushed the continuous loading of traps to higher and higher phase space densities. But all of this is not quite enough to deliver a continuously existing Bose-Einstein condensate or a continuous wave atom laser. And part of the reason is that all these experiments have been so far performed with alkalis and chromium, and these elements have rather poor laser cooling performance. In addition, BECs are incompatible with laser cooling. If you have a BEC, the atoms are essentially standing still, and if there's laser cooling stray light around, these photons might be absorbed by an atom in the BEC. The momentum of the photon will be transferred to the atom, it will have a speed of a centimeter per second or so, and then it's a thermal atom. So the BEC will just be depleted in no time. And that's of course bad, because I told you we want to have laser cooling close by to the BEC to accept this incoming stream of cold atoms. Now, we are working with strontium, and this element provides you with new opportunities. For example, we not only have a broad 30 megahertz wide blue laser cooling transition, but we also have a 7.5 kilohertz narrow red laser cooling transition, which can cool you to much lower temperatures. And we have a trick, a transparency beam, which we can protect the BEC from photons. And we combine this with a standard trick, the dimple trick, to create a BEC with special properties. First of all, to create this BEC, we removed all the entropy from the gas using laser cooling alone. And second, this BEC is in thermal contact with a laser-cooled gas cloud, which is very beneficial for creating an atom laser. Now, I want to describe you this experiment that we did in 2012, which is a baseline of the atom laser experiment, a little bit more in detail. So we start, of course, with an oven, slow the atoms down in a Zeeman slower, intermod, all operating on the broad line with transition. Then we switch over to cooling on the narrow line, and that brings you already to 1 microkelvin and a phase-space density of 10 to the minus 3, which is not bad, however not good enough. And why can't it be better? The reason is that in a magneto-optical trap, the lasers have to support the cloud of atoms against gravity. And for that, you need to make the lasers relatively intense. And then you have a lot of laser light going around and provoking multiple scattering of photons between these atoms, and you can't get your gas cloud really dense. However, if we transfer these atoms from the red mode into an optical dipole trap, they are levitated by the dipole trap, and we can now make our laser beam less and less intense and still cool to 1 microkelvin, but now at higher and higher density, reaching a phase-space density of 0.1, which is just a factor of 26 away from the critical phase-space density for Bose-Einstein condensation. Now, in the first experiment to create a BEC in this way, we just switched the laser cooling light off. Then we have 10 million atoms sitting in a large reservoir dipole trap. Now we ramped on an additional tiny dipole trap, the dimple. And atoms flow now from the reservoir into the dimple. And that will enhance the density of the gas, as you can see here in this density profile taken by absorption imaging. Just like the density of air at ocean level is much higher than the density of air on Mount Everest. But this gas will stay nearly at the same temperature as before, because the dimple gas is in contact with through elastic collisions with the reservoir gas, and the reservoir is huge. So the little bit of energy which we put into the system by switching on the dimple, that will just heat up this reservoir a tiny little bit, and we are still able to form a BEC. But now I told you we want to have a dissipative mechanism to accept new atoms into the reservoir. So we want to switch on laser cooling. As soon as we do this, the BEC is gone, because of all these heating phenomena and the dilution by multiple scattering. Of course, that won't do. Now, luckily in strontium, we can selectively inhibit atoms in the dimple from absorbing laser cooling photons on this narrow red mod transition. And we do this by shining yet another laser beam onto our sample. We call this a transparency beam, and it couples the upper laser cooling state with an even higher lying state and imprints an AC Stark shift onto this higher lying laser cooling state. And that means that here in the dimple region, the atoms are about 10 megahertz out of resonance with the 7 kilohertz line width laser cooling light. So these atoms just don't absorb any laser cooling light anymore. And you can make this visible by taking an absorption image on the laser cooling transition. And here you see in this density profile, there's a hole. And it's not that there are no atoms there. There are as many atoms in this sample than in that one. It's just that these atoms are transparent. And this enables now the gas to thermalize again. And here, in addition, the laser cooling cools the reservoir down all the time. So the little bit of additional energy that was put in by suddenly switching on the dimple and having these atoms roll down the dimple potential, that's just laser cooled away. And we need to detect, of course, this BEC. And in our machines, we don't have high enough resolution imaging system to see this BEC directly. So we do switch off all lasers and let the gas cloud expand. If you have a pure thermal sample, it will expand isotropically and give you rise to this Gaussian-shaped big background, the green cloud here. But if you have a Bose-Einstein condensate in your cloud, you have mean field energy, interaction energy, and the BEC will expand, or during the initial phases of the expansion, this mean field energy will be converted into momentum, and mostly in the direction in which we initially confined the BEC the strongest, which for us is the vertical direction. So if you look at the from the side, you see this famous smoking gun signal of a BEC, this elliptical density profile. Yes, and this BEC is a bit special. Yeah, it was produced by using laser cooling to remove all the entropy. But for us now, the most important part is that it lives inside a laser-cooled cloud of atoms. And that's really what we want for our scheme, to create a continuous atom laser, because this allows us now to throw cold atoms at this laser-cooled reservoir, and the laser cooling reduces the kinetic energy of this incoming beam of atoms and irreversibly puts these atoms into the thermal cloud around the BEC, where the atoms will eventually, by elastic collisions, find their way into the Bose-Einstein condensate. And ultimately, we want to outcouple an atom laser from the system, but that's for another time. Now I will explain to you how we built this system, how we were able to maintain this BEC alive for as long as we desired. So for that, we just need to make this additional ultracold beam of atoms arrive in this reservoir. And this beam, ultimately, it needs to originate, of course, from an oven where we heat strontium to 500 degrees Celsius, and the atoms initially are a few hundred meters per second fast. And to cool these atoms, we absolutely need the broad blue laser cooling transition. Only it can scatter the millions of photons per second necessary to slow these atoms down. However, our transparency beam trick doesn't work for this blue laser cooling light. So we built a new machine where we separated the vacuum chamber in a top part, in which we allow ourselves to use this blue laser cooling light, in a lower part in which we use only the red laser cooling light. And this is how the machine looks like in the lab. Yeah. And in the top part, it has just a Semans law and a blue mod, but it's a 2D blue mod, which lets atoms dribble downwards. We laser cool them on the red transition a little bit, so that the atoms really don't spread sideways, but just drop like a stone. And after they have arrived in the lower chamber, that's here, we have a vertically oriented Semans law working on the red transition, which slows the atoms and brings them into a steady state magneto-optical trap on the red laser cooling transition. And that's all nice and good, but it's not good enough yet for a continuous wave BEC, because there we have all these relatively bright laser beams on. We can't make a BEC here. So we transfer the atoms to the side. Let me zoom in onto this part. Here you see an absorption image from the side of the steady state red mod. And this here is our dipole guide. And we push the atoms from the mod into this dipole guide. And they fly with 10 centimeter per second velocity, a few centimeters to the side, where we have a teeny tiny third Semans law, also on the red transition, slowing the atoms down and pushing them very slightly and gently into this laser-cooled reservoir, which you see here. And this vertical gray thing that symbolizes the dimple. Now, that looks like this here in scale. I'll zoom in a little bit for you to see better. Here is the incoming beam of atoms. This is the Semans law turning around these atoms. And here you have the reservoir in the middle, this bulge, that is the dimple. And obviously we also switch on the transparency beam now. Now we need to look if there is a BEC in our system. Again, the resolution is not sufficient to see this yet in situ. So we switch all the laser beams suddenly off, let the gas expand and take an absorption image. And you see here the remnants of this really large initial distribution. These atoms come from the guide, from the Semans law region, the reservoir and the dimple. They are both here together. And in this cloud, there's nothing elliptical, so there's no BEC here. Now let's see if we can make a BEC. And we run a few experimental sequences now, switching everything suddenly on, waiting a little while, and then switching everything off and taking an absorption image. If we wait not very long, there are not many atoms in the reservoir and dimple. Then we wait longer, in the reservoir and dimple region, they fill up, and whoop, here, if you wait longer than 3 seconds, suddenly you see this elliptical feature appearing on our cloud. Could this be the BEC? What you also see is that nothing much happens anymore. We do know that this gas here is very dense, so there's lots of three-body recombination and molecule formation and also photoassociation going on. We have a lot of loss processes, but these are continuously compensated by the influx of atoms through the guide. Okay, so it's a steady state system. We can uphold this for as long as we want, with 5 minutes or more. Yeah. Now, we need to, of course, prove that this is a BEC. And how do we do this? We fit theory. So we start by fitting the simple-most model, assuming that it's not a BEC, it's just a thermal cloud. So we just take 3 Gaussians for dimple reservoir, the Semans law region, and then a Gauss-shaped tube for the transfer guide. And if we don't load enough, there's barely any fit residue. That describes our system really well. But if we have this elliptical feature for a long loading time appearing in our system, then there is a fit residue, just as you would expect if you had a BEC present. So we improve our fit by adding a Thomas-Formy profile, which is expected to describe the BEC, and now it fits both situations very nicely. And we also cross-check the size of the BEC is as expected, and it appears when you expect it, and so forth. And here you see the loading behavior, BEC atom number in blue, over loading time of our machine. There might be a little bit of swing in behavior, which could come from the red mod dynamics at the beginning. Perhaps it's also just technical noise that day. And then we enter a steady state. We, of course, want to prove that this BEC exists continuously forever, but we can't yet image it in situ. So the best thing we could do at the time was to just run many experiments, 208 experiments, always with 15 seconds of loading time, and look if there's a BEC present. And here you see the histogram of the BEC atom number. And indeed, on every single one of these runs, we did see a BEC well above our BEC detection threshold. Okay, so that summarizes it. We have BECs with 7,500 atoms. The replenishment rate of the is like 10 to the 5 atoms per second. The dimple and reservoir both contain about 1 million seconds, and the loading rate into the reservoir is 1 million atoms per second. Now, we analyzed all of this a little bit more in detail, also the dynamics of the BEC appearing, and we were not able to describe our data with fully thermalized distributions. And if you think of it, that's not too surprising, because we drive the system really hard. There are always new atoms going into this reservoir, and there's not enough time to fully thermalize them. If we assume in our model that we have higher than occupation of higher trap states and expected from a thermal distribution, we can fit our data very well. So this could be a signature of the driven dissipative nature of our system. And that might open an interesting research direction here, driven dissipative many-body physics. There are lots of proposals out there for interesting phenomena that you could observe. BEC purity oscillations, which is just essentially oscillations in the BEC atom number, phases with new types of critical exponents only accessible in driven dissipative systems, unusual quantum phases. And by the way, there are already driven dissipative BECs in other systems, exciton polaritron BEC, magnons, photons, where you can study this physics. But with ultracold atoms, we bring in new ways of manipulating the system and analyzing the system. And also there's another difference. Our system, in principle, if the lasers don't unlock or the strontium oven doesn't run out of material, we should be able to keep this BEC around for as long as we want. Whereas in these other systems, the particles are created with laser excitation. They just simply would overheat if you would drive it for too long. Okay, so what will be our next steps? So obviously trying to create an atom laser. The first simple method could be just using Raman transfer of our BECs to an untrapped metastable state. If you select the wavelengths of your dipole traps nicely, this could be done. But there, in this situation, the BEC is still surrounded by a huge thermal cloud, and we want to purify this a little bit better, so we need to cool better. And this could, for example, be done with evaporative cooling, for example, as shown on this slide, that you fiddle the continuous beam into a dedicated evaporation guide where the atoms slowly drift down and evaporate sideways till the radial harmonic oscillator ground state is macroscopically occupied. And now I want to show you, I asked Rodrigo, a PhD student on this project, to give you a little lab tour.
Hi everyone, thanks for coming to this virtual lab tour. Today we're going to show you the atom laser experiment here at the University of Amsterdam. So here is our atomic oven. Here we heat the strontium atoms to produce the hot vapor. The atoms travel through the Siemens lower axis, and then they are slowed down in our blue 2D mode. Now as we zoom in, the atoms are here, trapped and cooled, and they fall down to the bottom chamber. And it is in this bottom chamber where all the magic happens, and we've made the steady state BEC. Here in the closer shot you can see some of the optics that we use. Our transparency beam, and some of the mode optics. And some of the transport laser optics. So, thanks for coming. I hope you enjoyed this virtual lab tour, and I hope to see you again here soon.
So, okay, I'm back in the normal sharing mode. And yes, so this finishes the first part of my presentation. I showed you that we have created a continuous wave BEC in steady state. And Andrew, you might have some questions now.
Yeah, sure. Thanks, Florian, for the really nice first half of the talk and a really, really nice looking, fascinating experiment. So we have quite a few questions already. So I'll take a few of them now and a few of them at the end, maybe. So the first is a question from Bill Phillips. So he asks, besides the lack of CW atom lasers as an impediment to using BECs for atom interferometry, there is also the problem caused by atom-atom interactions, which are absent in optical lasers, at least in vacuum. Could you comment on this?
Yes, of course. If you, if you want to have an atom interferometer that works nicely, you have to overcome this challenge of interaction. So you could make this atom laser relatively dilute, at least at the end, so that the phase isn't disturbed too much. On the other hand, you could perhaps use these interactions also to produce a squeezed atom laser, and then it might be beneficial for atom interferometry. So these are the two sides of the coin here.
Okay, I think we'll come back to the squeezing question in a moment because we have a couple of questions about that. Before that, though, the second question is from Sandra Buob. I'm sorry if I'm not pronouncing the name quite correctly. Is the transition you use for the transparency beam also a loss channel in your experiments?
A little bit. It off-resonantly can excite atoms and create optical pumping to metastable states. So we can pump them out of this with repump lasers if we want to. But otherwise, no, it's not a lost channel.
Okay, so the next question is another one from Bill. Firstly, a comment that it's great to see multiple Zeeman slowers in such a nice experiment. And then the question is, laser cooling alone has famously failed to produce BEC on its own. The Dimple, at least for Bill, is a way of bringing in evaporative cooling. Although you didn't say it quite that way, is this a more sophisticated process, essentially still doing the final cooling to BEC by evaporative cooling?
Yeah, I mean, you could consider it, if you want, as a one-step evaporation process. However, you know, we really cool away, and that we cool away the entropy that is brought to the reservoir with laser cooling. So it's perhaps a little bit playing with words at some point. Also, in real evaporation, you discard these atoms, you let them drop away in your vacuum chamber. We don't do this. You could, of course, say you could recycle your atoms from the wall of the vacuum chamber and putting it back, but yeah. So there are elements of evaporative cooling in the Dimple trick, but not everything is happening there. Yeah, that's why I was a little bit careful with formulating this and just said we remove all entropy from our gas with laser cooling. And by the way, obviously the BEC is still formed by elastic collisions, just as usual in the Dimple.
So coming back to squeezing, you mentioned that interactions could be used to squeeze the BEC. Could you say maybe a few more words about how you might do that in your experiment, maybe as a future step?
Whew, this is way in the future. Squeezed atom laser. I didn't spend much time thinking about this yet. I mean, what you are exploiting is that the phase of the BEC changes with the atom number, with the density, and then that is just like a rotation, so to say, of your Bloch sphere. But no, I didn't think much beyond that for our machine.
Okay. And maybe one more at this point. So regarding the Dimple trick, in your experience, how large of a reservoir do you need compared to the Dimple for the reservoir to act as an effective reservoir for this type of setup?
So in the original 2012 experiment, there was a ratio of 10 in the reservoir and in the Dimple, and that was excessive, but it helped us to uphold our BEC for a very, very long time. And in the new system, we have the same number of atoms in the reservoir and the Dimple, so it's not really exploiting what you usually think of. I mean, usually in like about 20 years ago, when like Wolfgang Ketterle used the Dimple trick to pull to create a BEC in a reversible way, it was important that the reservoir is really huge. Otherwise, you would have heated up your system too much when pulling down the Dimple. But for us, it is not so important because we can laser cool the reservoir atoms.
Okay, there's also a comment, by the way, in the chat from Magic Levenstein protesting the comment that there isn't laser cooling to BEC. In that Vladimir Vuletic realized true laser cooling towards BEC in the Festina Lente regime.
Yeah, but elastic collisions were also important in that experiment for the final thermalization to BEC.
I'm guessing he was protesting more the phrasing of the question than your answer, which I also totally totally agree with. Okay, so we have a few other questions, but maybe we'll save those to the end and let you go on with the second part. Thanks, Florian. Looking forward to the second half.
Okay. Thank you. So I've shown you that creating this microkelvin coiled strontium beam in the dark was really important to provide this replenishment for the BEC. And it turns out that this beam is also very useful if you want to build a so-called continuously operating superradiant clock. Now, what is this? Let me first describe you a little bit more in detail how normal optical lattice clocks work. So you cool a sample of, say, strontium, put it in the magic wavelengths optical lattice, and then spectroscopically interrogate your sample, and that destroys it. So you have to produce a new sample, and during this time, you don't want your laser to drift away in frequency. So you stabilize it on an ultra-stable resonator, a macroscopic reference. Now, if you look at the scheme, you can see 2 points where you can improve things. You, of course, would like to have your atoms present all the time, not only intermittently. And second, these ultra-stable resonators, they are real engineering marvels, but they are also very complicated. For example, not easy to operate on a moving vehicle. You would like to simplify this. Just to give you an impression here about the best ultra-stable resonators that are out there. For example, you can use large ULE spacers. Then the frequency limit comes from thermal length changes of the spacer. The next step was then to go to silicon monocrystal cavities at PTB and Gila and operate them cryogenically at the zero expansion, at the point of zero thermal expansion of this silicon. And in these cavities, the limit comes from the thermal noise in the coatings of the mirror. So the next step will be to use crystalline coatings. These devices are absolutely amazing. You get sub 10 millihertz line widths of your lasers, but as you see, they are also a bit complicated. And superradiant lasers or clocks are a way to get similar performance, hopefully, from a simpler system or more robust system, or exploiting these really good resonators, even perhaps go beyond and make even more stable lasers. So how does a superradiant clock work? So in a sense, it's the inversion of a normal clock. In a normal clock, you prepare an ultracold sample of atoms, and then you shine a laser beam onto the atoms and see if the atoms get excited or not. You say you passively interrogate these atoms. It's a passive clock. In a superradiant clock, you prepare an ultracold stream of atoms, all excited to the optically excited state, and push them through the cavity mode and entice them to each emit one photon on the clock transition into the cavity mode. So here it is the atoms that actively emit photons into a laser beam that you use as your clock. And so this looks an awful lot like a laser. And indeed, it is a laser. It's just not a normal laser. In a normal laser, you use a gain medium, which has a profile that is much, much larger than the line width of the optical cavity. And the frequency of such a laser is given to you by the cavity. If the cavity somehow changes in length, the output frequency of the laser will change. In a superradiant laser, you choose an atomic transition that is way narrower than the line width of the cavity. And the frequency stability then comes from the ensemble spin of atoms. If the cavity length changes, the frequency of the outgoing light doesn't change very much. Yeah, it still changes a little bit if the cavity mode is not centered on the atomic transition frequency, but it's suppressed by a factor 1,000 or even more compared to a normal laser. And this is exactly what we want if you want to build a clock or ultrastable laser. So still, this cavity is pulling the laser's frequency around a little bit. So wouldn't it be best to operate this active clock without a cavity at all? Let's try this. Let's just produce a sample of 100,000 strontium atoms, put them all into the optically excited state of the clock transition, and wait for spontaneous emission to deliver us those clock photons. Now, the clock line is a mHz-wide. That's 2 minutes of lifetime in the excited states. That means you will obtain 100,000 photons within 2 minutes into 4 pi. This is pretty useless. You can barely detect these photons and certainly not determine their frequency. You need to somehow enhance the emission, and that can be done by superradiance. How is this working? Let's imagine we have n emitters, n atoms, closer to each other than a wavelength. And initially, let's say all these atoms have a random phase and emit randomly. Then the output power will be just n times the output power of a single emitter, nothing special. That's just what I said to you on the previous slide. It's unusable. However, if you somehow manage to phase synchronize all these emitters, then it's the electric fields which will sum up. And the power is the electric field squared. Now you get an output power which is n times more than in the first situation, and n is a large number, so that's great. However, we cannot place so many atoms closer than wavelengths cubed that would provoke chemistry and shifts of the transition frequency. We need to be a little bit smarter and spread them out, but imprint a phase pattern on these emitters in a peculiar way. For example, here in this situation, I placed these atoms half a wavelength apart and imprinted alternating phases on them. And if you sum up all these electric fields, you see this pattern. You see two strong emissions along the line of these atoms, and that's also enhanced by this factor n. Yeah, this is exactly what we want. Now the question is, how can we obtain this phase pattern here? And the hint at that comes to you if you look at the phase of the electromagnetic field inside a cavity. If the standing wave here in alternating antinodes has the electric field oriented downwards, upwards, so also 180-degree phase changes, just as what we desired these atoms to have. And this helps to establish superradiance. Imagine we have these atoms shown here as little Bloch spheres inside our cavity, and at some point some vacuum fluctuation will start provoking a spontaneous emission event, and this establishes a tiny electric field inside the cavity which torques the Bloch vectors of the other atoms, and just in the right way to obtain this phase pattern as is needed for constructive interference to enhance the emission. Of course, this is not happening one after the other. As I explained it, this is a collective effect. The light and the many-body Bloch vector here are really strongly locked together in the relevant regime. And okay, so a vacuum fluctuation starts emission of the light, and then all these dipoles will oscillate together and emit more and more light, stronger and stronger into the cavity mode. The photons, of course, leak out quite quickly because this is a relatively bad cavity. And at some point, all the atoms will have emitted a photon into the cavity and the laser pulse dies out. And that has been beautifully demonstrated in the group of James Thompson and Gilla on the millihertz clock transition of strontium. Here you see their data where you have these pulses of light coming out of their system. And you can see that the pulses are more and more intense the more atoms you put in there. This is this superradiant enhancement. But they are also relatively short. Now, this is really beautiful, but ideally, you would, of course, like to have the superradiant emission going on forever. How can this be done? For this, we can simply send a continuous beam of atoms through the cavity and prepare the atoms before the cavity in the upper clock level. And then if an atom enters the cavity mode, it will synchronize with the local phase of this electric field just in the right way, so that it will constructively interfere with all the other atoms that are emitting and enhance the emission. And this is very similar to a hydrogen maser. It's just that the hydrogen maser operates, of course, in the microwave regime, and we want to make this work now in the optical domain. And this is a complicated problem, which we are pursuing within the Quantum Flagship project iqClock, and we split the problem into 3 parts. And the first part is to build a superradiant, continuous superradiant laser on the kHz line width transition of strontium, and later on the millihertz line width transition. And the beauty of this is that you can make the machine work with a hot beam of atoms coming out of a simple oven. And the requirements for this to work is that the speed of the atoms on axis with the cavity may not be too high. And we need also an enormous flux of atoms through our cavity, such that always 100,000 atoms are in the cavity mode. And we hope that in our first machine operating on the 7.5 kHz line of strontium, we will obtain a line width of the outgoing laser light of 100 Hz and a power of 100 nanowatts. And that's how the machine looks like. Let's zoom inside. There's a powerful high flux oven down here. We transversally cool the atoms, have then velocity dependent pumping to a metastable state and to the upper lasing state. And then up here is the cavity where we hope to see the superradiant lasing. And this is how the machine looks like in the lab. And then in a second stage, we want to transition to the millihertz line. For that, you really need an ultracold beam of atoms because of the Doppler effect. You really need to confine your atoms in a magic wavelength lattice along the cavity lattice to suppress all motion, and that's only possible if your incoming atoms have a temperature of a few microkelvin. In addition, the superradiant ensemble, each atom there is in a superposition between ground and excited state. And that means since each atom has a ground state contribution, they are susceptible to laser cooling stray light photons. And if such an atom absorbs a stray light photon, it's projected to the ground state, and then it will take light out of the cavity instead of giving us light into the cavity. So that's why we need a strontium beam in the dark. And also we need a sufficient flux, but we think we can achieve this. And this, we might be able to push this to a millihertz line width laser with a picowatt of output power. We again split the task into 2 to de-risk the project. So in the first part, we will have a machine where we have a pulsed mod, and every 2 seconds we will move atoms from this pulsed mod through a conveyor lattice into a reservoir. And then it's from that reservoir that we try to extract a continuous beam, which will go into a ring cavity so that we can have enough atoms in it at any time. Yeah. We hope this will work already. It's certainly easier to make work than a continuous machine, but it will probably lead to atom number fluctuations in the cavity, which is not really the best for precision measurement applications. So ultimately, we would like to build a truly continuous machine. The top part here is a simplified version of the SM laser machine. We learned a lot building the atom laser machine, and we know now how to simplify all of this. And then we will fiddle the atoms into a transport lattice and into the ring cavity again. Okay, and I asked Francesca to show us the machine. Let's see.
Welcome to the iqClock lab. Today I'll show you a little bit what we have around us. So we are still in a building phase, so it's a little bit of a mess, but there are also good stuff. So let me start from our machine. We are building a kHz clock. So you don't see it from here, but the atoms are starting from an oven that is like below there. And they then travel vertically, and we use blue and red light, the blue you can see, to manipulate them. and prepare them for the final stage that is in a cavity that is more or less at this height, also a little bit of red, where they then are going to superradiantly emit, and this is the signal we are interested in. We use different optics. You can see here different distribution systems to prepare the lights we need, and we control the different stages thanks to software. So here it's in particular the one related to our experiment, and we also monitor the different lasers using cameras, and I'll show you where the lasers are. So first we arrived to the electronics cabinet. So here we have the different RF amplifiers and the frequency generators to control again the frequency of lasers and prepare them. And the real objects are here. So we have blue, as I told you, and red. And let me see, and I can show you. Okay. Oh yeah, thank you for this short introduction. Now I can show you other people working here. So perhaps we have our Camila. And our Stefan and Shen, and Shen in the other lab. So yeah, thank you for this very short tour, and I hope you enjoy.
So let's switch this off and back again to the normal presentation mode. So that's where we are. So here's a summary of my talk. I showed you how we made this continuous wave Bose-Einstein condensate, and I showed you where we are now in creating these continuous superradiant lasers and clocks. So these experiments are, the clock experiment is performed within the Quantum Flagship project of 6 industry partners and 6 academic partners across Europe, and we also enjoy nice collaboration on the kHz machine with Murray Holland's and Travis Nicholson's group. And we have 2 more machines in our group on quantum simulation with rubidium-strontium molecules, and we have strontium atoms and tweezers, which we plan to Rydberg couple for quantum simulation. And all of this is, of course, only possible if you have a good team of people all nicely working together. Here they are. And if you're interested in our research, we do have 2 open PhD positions and a research assistant position, and possibly more positions coming up in summer. So thank you very much.
Great. Well, thank you very much, Florian, for the really wonderful talk. And it was fascinating also specifically to see inside the labs. That was really great. So thank you to you and your group for all of that. So we had quite a few questions and comments through email and in the chat. Picking up on the discussion we had about laser cooling to BEC last time, Magic has added the clear comment that the entropy was taken away from photons, that clearly to reach the equilibrium state that things thermalize by collisions. But the cooling, of course, in Florian's experiment was indeed laser cooling. And we also got an email from Bill saying he completely agrees with that and apologizes for the phrasing of the question. And I also apologize for the phrasing of the question and agree. And actually, maybe when we post the questions, we should post a link also to the nice paper by Vladan and his group to clarify that aspect. We have another follow-up question from Bill asking to outcouple from the continuous BEC. It seems that the old NIST technique where you kick out the atoms via a Bragg process would be useful. Are you thinking along these lines?
Yeah, I mean, we are thinking along having a Raman process coupling us to the 3p0 state, the upper clock level. And if you use optical dipole trap with just the right wavelengths, the atoms will not be confined if they are in 3p0, They will just trickle down. So that might be a first approach of making an atom laser.
We also have a question sort of turning to the second half of the talk from Shu Chi, who asks, is the shot noise from the picowatt laser, sorry, is it too large for an optical lattice clock, or does it not matter in this particular case?
Too large? I don't know. I mean, we have this really low output power of perhaps 100,000 photons or so per second, and we beat it with a reference laser, and that tells us how far the reference laser is away from the nominal frequency it should have, and helps us to steer that laser. This is yeah.
Sort of following up on the questions of the potential limitations there, are there limitations also in that experiment from Raman scattering from the trapping lasers, in particular if it limits the coherence time of the excited state atoms to a few seconds, which would be below the sort of, if you like, 1/mHz scale. So what limitations do you see there in these experiments?
Mm-hmm. Yeah. So these atoms in the superradiant cavity, they don't live longer than 1 second in this cavity. So I don't think that additional processes which remove the atoms from the superradiant ensemble should be all that bad, yeah, because it's really the phase coherence is stored in all these atoms together, not in an individual atom, and they nicely should synchronize up if you feed new atoms in.
Okay. So we have another comment and question from Bill. Bill says all the optics is a drawer in the drawer is beautiful, and he says going to the superradiant mode still involves a cavity, although maybe with a lower finesse than a laser. But there seems that there's still cavity pulling. So for operation at 10⁻18 or better, is this still going to be okay?
Yeah. Okay. So. For the kilohertz line, we calculate that the cavity pulling factor is 10⁻3, so it's 1,000 times suppressed. And for the laser operating on the millihertz line, it could even be down to 1 million. It's really, really low. Of course, reaching that limit will require much more than just making a superradiant laser work on the millihertz line with transition. There's all kinds of technical effects like light shifts and so on that could change over time, which would inhibit you for stably reaching this line shift. But the cavity pulling itself should be manageable.
We also have a question sort of on a technical level on the optics and drawers, which indeed look really great. I was like, how stable is that type of setup? Does there have to be a temperature control on the cabinet? Do you use a temperature control there?
Not yet. So the trick. We invented this trick when we ran out of space in the atom laser experiment, and the trick we found there is to have these 2 centimeter thick aluminum boards on which we mount these optics. Don't make them too large, and then we put them on rubber feet so they're really decoupled from the drawers, and at least the temperature stability in our atom laser lab is sufficient that we don't need to realign this optics all that much. And there, it should be on the 0.5 degree or so level. The ones on the iqClock machine, indeed, perhaps we will ultimately have to install some kind of cooling system to make it a little bit better than what we have right now. But okay. Ask me again in a year or two when we have a little bit long-term experience with this new setup.
Okay. I think we'll take maybe just one final question, maybe asking, is there some future potentially in combining the first and second halves of your talk? Could you imagine, rather than using a cold atom beam, some use perhaps here in using a continuous atom laser to provide the atoms for the second half of the talk? And what would be the potential advantages, and what would you see as being the difficulties of doing that, particularly maybe thinking about Doppler broadening and various things that could come in?
Right. So far, I only was thinking about the inverse of this question, using Helmut Retzsch's proposal to create an atom laser in exactly the way as a superradiant laser. You would feed a thermal sample of atoms through the cavity, have cavity cooling going on, and get a superradiant laser out in one side and an atom laser out on the other side. Now, this question here was the other way around. Do we need an atom, or would we profit from an atom laser here? I'm not convinced that this would be really much better. I mean, it would, of course, perhaps lower the depths of the magic wavelengths lattice that we would need, because the atoms are colder to start with. That might be an advantage, but the flux will probably just be lower because it's more complicated to make an atom laser than a thermal beam of atoms. So I think the disadvantages are bigger than the advantages here.
That's great. So thank you very much again, Florian, for the really nice talk and the fascinating results. And yeah, I'll pass back to Sebastian.
Yeah, thank you also from my side, Florian, for a very cool and very clear talk. It was very easy to follow, I thought. So next week on March 11th, we will have yet another talk by Jeff Steinhauer talking about quantum simulations of cosmology. And thank you, Tao Wang, for suggesting this speaker to us. And you should certainly also check out our sister seminar, the virtual AMO seminar, where tomorrow they will have Nathalie de Leon speaking about nitrogen vacancy centers in diamond. And if you want to get notified about what we do, please go to our website, quantumscienceseminar.com, subscribe to our email list and our Google Calendar, and follow us on Twitter. And with this, I'd like to thank you for your interest, and we hope to see you again next week, same time, same place. Bye.